All right, so we're going to take a look at solubility product. This is another complex equilibria. So when I say complex equilibria, I'm talking about things that have more than just one side. So when we were looking at the first equilibrium problems, I started with some reactants. I produced some products. We figured out where the equilibrium lied. And then when we were looking at weak acids and weak bases, we did the same thing. Okay, and put this acid in solution, see how much base, see how much product I produced, and we determine the pH and so on and so forth. And then we looked at buffers. Buffers were more complex. There's both things present. We have to do some kind of calculations. Solubility product is the same concept. Actually, this is easier because there's certain, you'll see why in a little bit. But the idea is simple. So if I have a beaker with some amount of water in it, okay, and I deposit some kind of solid in that water. Okay, so let's say that we're going to say that this is AgCl, because that's the example that I'm going to use below. So I've deposited AgCl into solution. Well, what I do know is it is, first of all, if we look at this, the table, the solubility table, we're going to find out that AgCl is considered insoluble. Okay, so it's not going to dissolve in the water. But that's not really true. When I say insoluble, I say to the naked eye. So I drop some AgCl in solution and none of it dissociates. But what we actually do see is we see a small amount of this. So we see these Ag plus ions, and we also see Cl minus ions enter solution. Very few, again, to the naked eye, we are going to see nothing change because it's considered insoluble, but we do get ions to form in solution. So although we have said, oh, things are insoluble, that's not quite true. When we have a solid in solution, they always dissociate to some degree, to some small degree, to some very minuscule degree, but they're still going to dissociate. So when we talk about the Ksp, which is solubility product, we're going to be talking about saturated solution. This, as soon as I put a solid in solution, it is now a saturated solution, assuming there's still solid on the bottom. If I asked you to prepare a saturated solution of something for me, how would you do it? Well, what you'd simply do is you take some water, you would add a bunch of salt and dissolve as much as you can. If there's solid on the bottom, great, your solution is saturated. If you don't have solid on the bottom yet, if you don't have solid that's still undissolved, you just add more salt. You add more solid until it stops dissolving. And once it stops dissolving, now the solution is saturated with the maximum amount that it can actually hold. So let's consider the equilibrium of the above. So AgCl solid is in equilibrium with Ag plus aqueous plus Cl minus aqueous. Okay, so this is what we have in solution. Again, if we kind of take a close look at what we're actually seeing, if I have a bunch of my AgCl, which are just positive and negative ions, okay, there we go. And I introduce a water molecule. The negative portion of the water molecule and the positive portion. The negative portion of the water molecule here up top is going to attach itself to that positive ion. And if I had another water molecule, the positive portion is going to attach itself to the negative, and they're just going to yank them out into solution. So what we end up with is we end up with this positive ion that is completely surrounded by oxygens. Because remember, the oxygen is the negative portion of the water. And so I'll just create one, right? There's the H2O. And I'm just going to create H2O for the rest of these. They're bound like that first one, but I'm just going to save myself some time and do it that way. Okay, so they're all bound and they're all kind of pulling that in. This area around the outside, this is known as a solvation shell. it solvates, it creates this shell around the ion and it pulls it into solution. Okay, and it just keeps plucking those off. So we have lost this one because it's gone away. We're going to lose this one because it's going to go away, and it's just going to keep pulling these. The water is going to keep pulling these off until it gets to a saturation point, and then it's going to stop. And the same thing is going to happen, the same but opposite is going to happen for the hydrogen. So for the negative ion, instead of being pulled off by the oxygen, what we're going to see is this is going to be pulled off by the hydrogens, because that's the positive portion of the water. And by the way, typically you're going to see six things attached, and because it forms an octahedron. Sometimes those hydrogens are from the same water, sometimes they're from different waters, but ultimately you end up with some version of this. And again, this one also has a solvation shell as well. Okay, so that's it. That's what happens. AgCl dissolves into Ag plus and Cl minus. Saturated solution are considered weak electrolytes. So now what we have to recognize is we have a couple of different types of electrolytes. So we have a strong electrolyte. Those are the soluble salts. The soluble salts on our solubility table. Okay, there's no equilibrium. They are 100% product. So that means if I put sodium chloride in solution, I have 100% sodium ions and 100% chloride ions. Nothing interesting there. But the weak electrolytes, much like our weak ions, our weak acids, are going to have some percentage. They are going to be the insoluble salts. So something like AgCl, for example, they are going to have an equilibrium where they're forming both products and reactants. So both of those things are going to be present at the same time. So let's write out the equilibrium expression then. So again, we're going to call this Ksp, and the Sp stands for solubility product. So Ksp is equal to the concentration of Ag plus times the concentration of Cl minus, because again, it's products over reactants. What you're going to notice is there is in fact no denominator here because AgCl is a solid, right? So the fact that AgCl is a solid indicates that it's not going to be an equilibrium expression. So there is my equilibrium expression for, or the Ksp for that insoluble salt put into solution. So this is called Ksp. So write the equilibrium expression for these three. I'm going to do these three right now, but write out the equilibrium expression for these three. And I encourage you to write out the equilibrium for each of these first, and we'll go from there. So write out the equilibrium. I'm going to pause it. It's going to resume right away, but figure out what the Ksp is for each of these are. Okay, so what we got, barium sulfate. Barium sulfate is going to break into barium 2 plus, aqueous, and SO4 2 minus, aqueous. The Ksp is equal to concentration of barium 2 plus, concentration of SO4 2 minus. That's it. That one's simple, straightforward. How about MgCl? Mg plus or 2 plus and 2 Cl minus. So I'm going to stop writing aqueous here just to move this along a little bit. The Ksp is equal to concentration of Mg2 plus, concentration of Cl minus squared. Why do I not actually need to write that out for this one? Think about it for a moment. Because this is a strong electrolyte. So this is going to be a massive value. So this is going to be, I don't know, 1 times 10 to the 34 or something like that. That's a guess. But what that ultimately means is this is 0% this, 100% product. So we really don't need this because ultimately all of it is in fact going to be product anyway. These are going to be important or they're going to be relevant, but we'll see why later. For this last one, we're going to have Al3 plus and CO3 2 minus. I have 2 aluminums, I have 3 carbonates, and here's where the KSPs get a little bit tricky. KSP is equal to the concentration of aluminum 3 plus raised to the second, because the coefficient goes up there, and carbonate CO3 2 minus raised to the third. Okay, but either way, we're just doing it based on the balanced chemical equation, as we always do for equilibrium expressions. That's it. That's my KSP. Very simple, very straightforward. We don't have a denominator, which makes life significantly easier. And we pretty much never have to use the quadratic. And that's what we always try to avoid. So let's talk about the idea of KSP versus solubility. So solubility I talked about, and I created that chart, and you saw that chart for KSP, for solubility. And these two things are not the same. They're related, but they're not the same thing. So first of all, let me rewrite. AgCl as a solid is in equilibrium with Ag plus aqueous plus Cl minus aqueous. Okay, and the KSP for this, KSP is equal to the concentration of Ag plus concentration of Cl minus. There we go. Okay, so looking at these two things. So we have two concepts, the KSP. Let's look at just this right here, molar ion concentration. So what I really want to know is when I'm talking about the solubility of this thing, really the molar solubility, what I want to say is if I drop AgCl into solution, how much of it is actually going to dissolve? Okay, and that's unrelated to KSP. I mean, it's related to KSP, but it's not quite the same thing. So KSP to molar concentration of ions. So the idea here is essentially that we want to go from KSP into solubility. Okay, in order to do that, what we have to recognize is, first of all, KSP is not equal to solubility. What is KSP? KSP is just the equilibrium constant. It tells you how much of it dissolves. KSP has no units. But solubility does, because solubility has units, can be measured in moles per liter, which is just simply molarity. Okay, shows the solution as it dissolves, grams per liter, or grams per 100 milliliters, which is a weird one, but it's pretty regular. Grams per gram, or weight percentage. So we have a bunch of different options, okay? And then finally, the molar concentration of ions provide the value of X, which is equal to molar solubility. And this is going to make a little bit more sense later. Okay. And just quickly, the X is really what X is equal to is the molar solubility, or yeah, the molar solubility on the ice tables. So solving for X is going to give us our molar solubility. So that's right here. That's our value for X. So essentially what I want to say is, all right, so I have some AgCl and I dissolve it in solution. For every one of these, I'm going to get 1 Ag plus in solution. So when I ask you what is the molar solubility of this salt, it's based on how many X ions I get into solution. So for every one of these, I get one of these. That's why X is going to equal to the molar solubility. So going between the molar solubility, which is just the X on the solubility table, to the mass solubility, we just simply have to have the molar mass in grams per mole. Because up here, I have grams per liter. And the molar solubility is in moles per liter, okay? Molar concentration of ions, so the idea here is, okay, the KSP is going to give you the overall equilibrium value. The molar ion concentration is going to give you, all right, well, what's the total concentration of ions that I have in solution? Molar solubility is, all right, well, how much of this did I actually turn into that And then mass solubility is just going to give us more practical numbers, something we would actually use in a lab. Okay, so these things are not the same, but they are related. That's kind of the end game here. So without doing any calculations, predict which of these compounds has the greatest molar solubility in solution. So first of all, what do we know about values of Ksp? What we know is the smaller the number, the lower the Ksp equals less product. Okay. So what that means is AgI has the lowest product, meaning it has fewest ions in solution, equals the lowest molar concentration or molar solubility. That all seems great and fine, but we have to recognize that this is a 1-to-1 ratio. So if I have AgX, I am producing Ag plus and X minus. But if I have something like, I don't know, some metal chloride, that metal 2 plus and the 2 Cl minus, all of a sudden the Ksp for this becomes M2 plus Cl minus squared. Basically, the value of X here is going to depend on the squares. So you have to watch out for this. You can't assume that the lowest Ksp, if the ratio is not the same, is going to be the one that's least soluble, because you can run into situations where you have a lower Ksp value, but because of the number of ions in solution, that changes things, right? So you might always have to do that calculation, or just recognize that we need the same, we have to compare apples to apples, right? I need them to be the same number of ions in solution, or what we're going to put in solution, in order to make sure that my solubility is in fact what it's supposed to be. So again, we can do two types of calculations here. Calculate Ksp from solubility, or I can give you Ksp and you can solve for the solubility. So calculating Ksp from solubility, let's take a look at this. So for a saturated solution, all right, so a saturated solution of silver chromate. So right away, calculate the Ksp for this compound. So first thing I need to do is I need to write out the equilibrium expression, because that's always what we do with equilibrium. Ag2CrO4 solid is in equilibrium with 2Ag plus aqueous plus CrO4 2 minus. Okay. Oh, it's not showing up. Okay. There we go. Okay. And of course, we're going to write out the Ksp for this. Ksp is equal to, oh, no fraction, concentration of Ag plus squared over times concentration of CrO4 2 minus. There is my Ksp. We're going to create our little ice table, as we always do. Okay, initial change equilibrium, and we know this whole thing's in molarity. So what do we got? So what do we know so far? So saturated solution, again, that's the saturated solution of silver chromate. That gives me an idea that this is in fact the thing, and it's saturated solution, whatever it's saturated solution of, that is the Ksp involved. Analysis of the equilibrium solution, silver ion concentration of 1.3 times 10 to the negative 4. Okay, so silver ion concentration at equilibrium is silver ion concentration is 1.3 times 10 to the minus 4. Okay, a couple of things. I don't really care about any of those numbers. We just know that there's enough to make a solution saturated. Okay, so we don't have to know anything more about the silver chromate, because we have enough to make it soluble. Okay, I don't have any of my starting materials. And so now what we can recognize is, okay, so for every, I know that I am going to gain 1 plus 1.3 times 10 to the minus 4 ions of silver, because that's what I see in the equilibrium mixture. So how much chromate do I gain? Well, again, this is an X and a 2X thing. So I gain 2X amount of this, meaning I gain X amount of that. So how much do I gain from the, how much chromate do I gain? It's simply plus 1.3 times 10 to the minus 4 divided by 2, right? Which is turns out to be, and just to make numbers easy, 6.5 times 10 to the minus 5. Right, so 1 order of magnitude different, but 6.5 times 10 to the minus 5. Great, so that's the calculation. Again, it's really easy to get those values if you're given equilibrium values. Now, let me just plug these values in. So equals concentration squared and then concentration. So 1.3 times 10 to the minus 4 molar times 6.5 times 10 to the minus 5 molar. You do those calculations and what you end up with is 1.1 times 10 to the negative 12th. There's no unit for this. That's my KSP. Boom, problem solved. That's solving for KSP. Easy enough, okay? So that was the KSP. What is the molar solubility? Oops. What is the molar solubility? Again, molar solubility is just the X value, or molar solubility is how much, how do I say this? How much of the Ag2CrO4, how much of the solid I lost, right? So for every one of these, I'm gaining 2 Ag. All right, well, that's not a good comparison because this next one, for every one of these, I am gaining one of these. So if I have 6.5 times 10 to the minus 5 molar chromate in solution, what that means is my molar solubility for this substance is going to be 6.5 times 10 to the minus 5 molar, which is, again, just the value of X. That's the molar solubility. All right, well, what is the mass solubility? Well, if I know that I have 6.5 times 10 to the minus 5 moles per liter, I simply say, well, what is the grams per liter? 1 mole of silver chromate. Let me look it up quickly. Molar mass for silver chromate is 331.73. Moles cancel, and what I am left with is silver chromate. And so let me get my calculator out here. So if I take 6.5 times 10 to the negative 5 minus times 331.73, I have 0.0, let's see, 2 sig figs, 22 grams per liter. There's my mass solubility calculation that I just did. Does that make sense? Okay, so that's the mass solubility of how much of this I lost when I actually put it into solution. So it's a 1-to-1 ratio with that. So we always use X as kind of the molar solubility, and then we convert molar solubility to mass solubility using the molar mass of the substance, in this case, Ag2CrO4. Good, okay, easy enough. That's what we're looking at. So for this next one, so the KSP, and you should have this, by the way, and this is a good opportunity for me to show you that at the very end, the very last 2 pages of this, you're going to see that we have, I've made a chart of all of the KSP values that we actually have. So here are all the different KSP values. These are, you would always be provided these, or these are the ones I would expect to use, or some version of this, but they're all here, okay? So you should have you should be able to look anything up you need for any of these problems that we're doing in class or otherwise. So for KSP for calcium fluoride, okay, so calcium fluoride, I'm going to give you this value is 5.3 times 10 to the negative 9. So in this case, I am giving you KSP, and I want to know the solubility. That's what we're solving here. KSP2 solubility based on that KSP that I'm providing for you. Okay, so let's take a look. Same exact thing, the KSP for calcium fluoride, meaning the first thing that I need to do is I need to write out the equilibrium that I have for my calcium fluoride. And both of those are aqueous, okay? And then we're going to create a little ice table. It's a molarity, initial change equilibrium. Okay, my KSP is equal to the concentration of calcium 2 plus times the concentration of F minus squared. My KSP was equal to 5.3 times 10 to the minus 9. Do I have any other information? So I've got given KSP, and that is it. I am looking for the molar solubility eventually, so this is all I'm given. So I don't care about the solid because it's not an equilibrium expression. I know I start out with 0 calcium and 0 fluoride. I gain X amount of calcium, and I gain twice as much fluoride. So for every 1 calcium, I gain 2 fluorides. Easy enough. So that means at equilibrium, I have X amount of calcium and X amount of fluoride. Perfect. Meaning I can just plug these guys in. Again, I want to make sure that I am doing the proper thing. And this is really where people tend to mess this up. So calcium is X raised to 1. And then the fluoride is 2X raised to 2. And so from here, we get to solve some math. So I'm going to say that I have X times what is 2X squared becomes 4X squared, okay? And now we're going to multiply those two things together. And so I have 5.3 times 10 to the negative 9th. 4X times 4X squared becomes 4X cubed. And let's solve for X. So I'm going to divide both sides by 4. And once I divide both sides by 4, I end up with 1.3 times 10 to the negative 9 equals X cubed. And then I'm going to take the cube root of both sides. Taking the cube root of both sides gives me a value of 0.0011 is equal to X. Again, the X value is my molar solubility. So molar solubility, sorry, we can do the ion concentration first because I have those values. So now that I know this, so X is equal to 0.0011. So that means the concentration of calcium 2 plus is equal to 0.0011 moles per liter, or just simply molar. And that means that the concentration of F minus is equal to 2 times that. So 2X. I guess I'll just move this down. Let's separate this a little bit just to show equals X. This is equal to 2X, 0.0022 molar. This right here is my concentration of ions. Great, that's my concentration of ions. But of course, what I really want to know is I want to solve for some molar solubility. So molar solubility, X equals molar solubility. Which is equal to 0.0011 molar. That right there is my molar solubility. Okay, so a couple of things. That is my calcium ion concentration. The fluoride concentration is there. This is my molar solubility. And then the final step is figuring out what the solubility in grams per mole. So if I have the X value is 0.0011 moles of the calcium fluoride per liter multiplied by the molar mass, which is 78.07 grams per mole. Moles cancel. And what we're left with is 0.086 grams per liter of the calcium fluoride. And this last one here is my solubility in grams per liter of calcium fluoride. Okay, that's solubility. Perfect. And so that's it. We have solved our solubility. We have all of our answers. So that runs the whole gamut from my KSP to my concentration of ions to my molar solubility to my, and we did it the other way around. Here, I solved for KSP and then showed molar solubility, which we could have gotten initially anyway. Okay. All right, good. So I got a bunch of problems here, so you're going to have to add an extra page or two, and I'm going to let you guys do these. But what is the KSP of iron hydroxide if the concentration of iron is 1.2 times 10 to the minus 5? What is the solubility of cadmium carbonate if the KSP is 5.2 times 10 to the negative 12? And the calcium phosphate, you can look up the KSP, should be able to find it in the table below. And we're going to move into factors affecting solubility next. So that's the next video coming up.